So I'm Mark Johnson. I'm an electrical engineer, but I'm trying very hard to make this talk not for electrical engineers. I'm trying to make this talk be as free of mathematics, as free of equations, as free of engineering mumbo jumbo as possible. That's my goal. So that's why the title is Transistor Matching for Woodworkers, Musicians, and Record Collectors, not transistor matching for other EEs. Okay, next slide. Okay, so the big idea is I want to make it easy for anyone and everyone to match transistors. And we've got hardcore EEs like me. There's speaker builders, there's record collectors, there are guitar players. They don't care too much about mathematics. They don't care too much about the underlying engineering equations. They just want to match their transistors because matched transistors give lower distortion and lower output offset. And the output offset is important because if it's too high, it can hurt your woofers. So here we have a little circuit board. You'll have it in your hands in minutes. That helps you do transistor matching of a particular kind. We're doing bipolar transistor matching and the parameter of one stick. So yeah, here's what's going on. When you get the board in your hands, you'll see that it has a place for two dip sockets that are 10 pins each. And 10-pin dip sockets are extremely rare and extremely expensive. So an alternative is to take SIP sockets and break them off at the 5 position point and just put them in there. So I'm distributing these SIP sockets so you don't have to buy dip sockets. And then afterwards, if you want me to tell you where I bought them on eBay, I will. It's not a secret. I think I got 150 of them for $5. Okay, so we're going to be dealing with bipolar transistors, and the parameter of bipolar transistors we're going to be matching is VBE. Next slide, please. Okay, what is VBE? Why does it matter? At the beginning, at the very front end of many, if not most, amplifiers, you have a circuit similar to this. You don't have to memorize this circuit because I'm going to wave my hands and pretend like that's proof. The input voltage is applied across these two transistors, and the assumption of this circuit is that these two transistors are identical. The circuit is designed to work with identical transistors. Sadly, when you buy these transistors from DigiKey, 10 transistors for $1.20, they're not necessarily perfectly identical. There's a slight mismatch between them. That's just the way they roll off the factory floor. So because the transistors are not identical, the circuit doesn't work perfectly as designed. And the goal of matching is to get them as close as possible so that you can get as close as possible to the goal of ideally matched transistors. Next slide, please. Okay, so what we're going to do is we're going to match VBE. That's going to lower distortion, particularly even order distortion, second and fourth order distortion, and it's going to reduce offset at the output. Now, the cool thing is we have labor at $0 per hour. Sony doesn't have that. So we can match transistors and it doesn't cost any extra money. Sony, it would cost them money to match transistors, or anybody that's in high volume, price sensitive manufacturing is probably not going to do matching. So here's where we have an advantage over the big guys. You can use this little board that you just got for free, never mind the cost of the ticket from Chicago, and an hour of your time, and you'll get much better transistor matching than Sony could ever hope for. Okay, so a few examples from the DIY Audio Store catalog that can directly benefit from this board that you have in your hand right now. The Honey Badger amp has a bipolar transistor input front end. The VFET amplifier that Nelson Pass is going to be talking about later today has a couple of input stages that have bipolar transistor inputs. And then there's a bonus PC board. I sure hope we have time to talk about it today. Okay, so this board is called Yes, It Will Drive an F4. And it has a matched pair of transistors on it, and we're going to do the matching. Okay, how do you do it? You use a test jig. The test jig is the board in your hands. The big secret of this board is precision resistors are cheap. So instead of having precision current sources, or some matching jigs have 25-term potentiometers and you have to go in and get it right. And every time you take it down off the shelf, you have to get it right again. No, just pay 63 cents for precision resistors and the problem is solved. So we're going to put identical currents through these two transistors. We're going to connect them as diodes. And that's not necessarily because connecting them as diodes is the best, but it's the most flexible. So when you connect them as diodes, NPNs go this way, PNPs go that way, and you get to reuse these super expensive 63-cent resistors. So that's what the circuit does. If you look at the little board in your hand, it says NPN on the bottom, PNP on the top. It's the very same thing, just with the wiring reversed. So the VBEs are here, and the difference between the VBEs is presented on these two terminals. So you just attach these two nodes, carefully brought out as a terminal block on your circuit board, connect it up to a digital voltmeter, and presto, you are reading the mismatch, the difference in VBE between these two transistors. And it's directly read. You don't have to do any math. You don't have to punch something on your calculator. The DVM gives you the mismatch directly. Here's the circuit board. The reason why it's a 10-pin DIP is that's the permutation you need to deal with every possible pinout on a transistor. So emitter base collector, emitter base, you can go this way, you can go that way, etc. So you plug in the transistor. I happen to be right-handed. So what I like to do is to plug in the device under test on the right. And over on the left, we plug in a transistor called the reference transistor. Let me talk about that. We're not going to be doing testing of pairs. We're going to be testing individual transistors versus a reference unit. So you take a transistor, pull it out of your bag at random, it doesn't matter, but mark it. I recommend marking it with a little dot of red nail polish. That way you can find it if it falls on the floor. You can determine which one was my reference transistor if you stop and then start again next Saturday or something. So reference transistor goes on the left if you're right-handed, and then the transistor under test goes on the right. And what we do is we measure the mismatch between device under test number 1 and the reference transistor. Write it down, scotch tape it to your little notebook, put in transistor number 2, write down the mismatch. Now here's the cool idea. If transistor 1 and the reference guy differ by 3 units, and transistor 2 and the reference guy differ by 3 units, then transistor 1 and transistor 2 differ by 0 units. So you have a match. So we've matched 1 and 2, even though they've never even met each other. So that's what we're doing here. Now, we're trying to get precision in measuring delta VBE, which means we need a relatively precise meter. I recommend basic accuracy of 0.1% or better, and I recommend one that'll read tenths of a millivolt or hundreds of a millivolt. I bought one on Amazon last week that I can recommend. It cost $50. I'll be glad to show it to you. I have it here. But there are plenty that do that and more. And if you have a benchtop multimeter that reads 5 digits, 6 digits, 7 digits, you're good. And if you have a handheld that reads 4.5 digits or so, just look at the specs and see whether it's this good or better. Now, if you have a crappy meter, you can still do matching. You just can't do excellent matching. But you can do better than Sony, even with a Harbor Freight meter. Okay, next slide. Oh, I'm sorry, would you go back? I neglected to say something. This thing is designed to run off a 9-volt battery. That way, you don't have to be in your laboratory with all your test equipment. You can do this on the kitchen table while you're watching football or something. The total load current is only 3 milliamps. So that means you probably get 100 hours out of a cheap non-alkaline 9-volt battery. And you probably get 200 hours out of an alkaline 9-volt battery. And I feel sorry for you if you spend 100 hours doing transistor matching. I recommend that you spend more like an hour and a half doing transistor matching. But the thing is designed that that won't use up your battery if you do. Okay. That's what's great about it. What's lousy about it? What's lousy about it is it's slow. And that's a direct result of the bipolar transistor itself. Bipolar transistors are incredibly temperature-sensitive devices. I'm going to say an equation out loud, and then I'm going to pretend I never said it. The temperature coefficient of VBE of a bipolar transistor is 2.2 millivolts per degree C. So if the temperature changes by 1 degree C, VBE changes by 2.2 millivolts. That may not sound like a big deal, but we are aggressive sons of a gun, and we're trying to match to a half a millivolt, which means we need better than a quarter of a degree C of matching. And so when you plug these boogers into the test jig, they're not exactly at the same temperature, and it takes a while for them to equilibrate to the right temperature. And in my experience, in my house with my air conditioning, et cetera, it takes about 1.5 minutes or 2 minutes. So pragmatically, what that means is that your throughput is going to be about 25, 30, 35 transistors tested per hour. Now, the good news is that if you have the same luck as I had buying transistors from DigiKey and Mouser, if you test 25 transistors, you're going to get 6, 7, or 8 that are matched within a half a millivolt. I'm sorry, 6, 7, or 8 pairs that are matched within it. At least that's my experience. I think 6, 7, or 8 pairs is going to be plenty for any one particular project. So an hour of your time gives transistors a lot better match than Sony's. Is there a question? Don't do that. Yes. Yeah, the answer is yes. Now, I'm not the only person that knows this. You know, now all of us know this. And people have tried to solve this in a variety of ways. One way that people try to solve this is to put transistors in some sort of a liquid bath that circulates, that, you know, gets temperature equilibration faster. Some people try and do it in a fan. There's a piece of gear used in semiconductor testing called a thermostream that blows air of a given temperature at incredibly high velocity. And so if you have incredibly high velocity air at, let's just say, 40 degrees C, then the reference unit and the device under test are going to get to 40 degrees C in a bigger hurry. But I don't want to do that. I'd rather waste 90 seconds of my life and all of your lives rather than buy that expensive piece of equipment or, you know, dink around with water baths or oil baths or fluorinert baths. Or you could clamp them onto a cold plate or a hot plate or something. All of those are experiments that I invite you to do, and I certainly do hope that you succeed, but I'm not even trying. I'm just going to accept 25 or 30 transistors an hour. Very slightly. Okay, so I should have said, if I happen to get a question about engineering, I'll smile and say, let's talk about that at lunch. Let's talk about that at lunch. The answer is yes, it is possible. They vary by a few percent. No. Okay, next slide, please. Okay, so here's an example of device under test versus reference. We have a reference unit on the left. Remember, I'm right-handed. So here on the left, we plug in the reference unit. The reference unit is a person born in 1970. Here we plug in a device in the device under test. This person happens to have been born in 1975. So the age difference between the unit under test and the reference unit is 5 years. Okay, so we put it over here and we round down 5. Then we plug in a different reference unit and we say, what's the age difference? Well, this person also happens to have been born in 1975, so the age difference is 5. So we go over here and we write down 5. We notice that this 5 is equal to this 5. Therefore, the difference in ages between these two and between these two is the same. So these two match. Even though they'd never been in the room together, even though we didn't test them at the same time, all we did was compare them to a reference unit, and we discovered that they match. Okay, apologies to Hollywood. All right. There may be people in the audience saying, Mark, I don't know you. I don't know why I should trust you. Yeah, you gave me this board for free, but I don't trust the board. Or I'm not convinced that this whole business about reference units is reliable. And so the good news is you don't have to trust me. Once you have identified potential matches, you can then take device A that is reputed to be matched to device B, plug them both into the board, and actually measure the VBE difference between them and see, are they matched? And if you're really anal, then you can say, but wait a minute, this measurement apparatus might be imperfect. It might be reading 0.3 millivolts error, but because the measurement apparatus itself is flawed, the right answer might be 0.4 or 0.2 or something. So what do? You measure them this way, then you swap them, and you measure them again, and you take half the difference between those two measurements, and that's the true mismatch error. And I have done that, but I don't know you, Mark. Why should I trust you? You do it. Go ahead and match up 25 transistors, get yourself 6 pairs, and then do this comparison. And I predict that after you do the comparison, you'll say, Mark was right. He's not as dumb as I thought. And now that I've done this once, I'm going to trust the reference method, and I'm not ever going to do this again. But I'm not telling you not to do it. I'm telling you, please do this, and that'll give you comfort that this procedure works. Yes, a non-engineering question.
Like on a small system that would have noise in them. And what you've done is explain a very practical way to correct for the noise inherent in any measurement system.
Great. Okay, let's have the next slide. All right, so this isn't the $49 meter that I talked about. This one is more expensive because it plugs into the wall, but more importantly, it has a backlight, and that photographs better. So here's the matcher. The previous revision of the circuit board was red. The ones that you have are black, but it's the same design. Here's a 9-volt battery. Here's the meter. And this guy, after 120 seconds, got to 0.3 millivolts. That's darn good. There's plenty of op amps for sale that don't have input offset this good. Next slide. And in true semiconductor fashion, I present the best measurement ever seen. And I say, typically, we see 0.08. Yeah, this is the best I've ever seen. All right, here's the schematic. You don't have to write anything down. I'm going to put all of this on the DIY Audio website. I hope there's no surprises on it. There's a 5-pin socket for PNP, 5-pin socket for NPN. Here's a precision resistor. Here's a precision resistor. Wow. I'm really sorry. The resistor bodies have disappeared. The values are here, but the little rectangle that says, hey, I'm a resistor is gone. Similarly down there. But it's the same circuit that we discussed before, and you'll see it online again. It's a pair of precision resistors, a pair of sockets. The 9-volt battery, as it discharges, gives lower output voltage. I compensate for that by using a cheap voltage regulator. So it could be 9 volts in, it could be 8 volts in, it could be 7 volts in, it could be 6 volts in. Doesn't matter, you're going to get 5 volts out. So you're doing a constant measurement at 5 volts, regardless of the state of your battery. Next one, please. Okay, so since Jim says I have time, I'd like to talk about a little bonus, a new circuit board that I designed specifically to show off matched bipolar transistors. It's a front end for the first watt F4 amplifier. And if you don't know the F4 amplifier, it's a follower. It has a voltage gain of 1. It'll produce a 20-volt peak, 40-volt peak to trough output sine wave, but you have to give it a 20-volt sine wave to make it do that because it's unity voltage gain. So there aren't very many DACs, or for that matter, preamps, that'll produce a 20-volt peak sine wave. So what is needed is some sort of a front end for the F4, and this is an example of that. However, we're lucky. To get 20 volts output, the F4 internally has 23-volt supplies. So all we have to do is to make a front end that uses 23-volt supplies to make 20-volt outputs. Piece of cake, right? Yes. Okay, let's go ahead. I'm going to be showing a relatively small printed circuit board that has holes spaced 40 by 80. You may or may not recognize that. That's the DIY Audio Universal Mounting Standard. So this board can actually stack as a double decker directly on top of the F4 and use the F4 mounting holes. You just unscrew the screws, put in spacers, screw them in the top, and you're all done. You have a double decker. And it uses the same power supplies as the F4. So that's my idea. You guys are a lot more creative than me. I'm sure that you'll come up with other ideas. You can put this little board anywhere you want in the F4. It doesn't have to go on top of the amplifier PCB. That's just my thought. I'm sure you could mount it on the front panel. You could mount it on the base plate. You could do whatever you want. The board that I'm going to be showing you has a voltage gain of 26 dB. That's 20x. Now you only need 1 volt in to produce 20 volts out. Preamps will do a volt out. DACs will do a volt out. Streaming devices will do a volt out. So now you have a way to drive an F4 with this little board inside from any source you want. Go ahead, please. So here's the double-decker stack. That's the, yes, it can drive an F4 front end. And here's an F4 board. I don't have a populated F4 board. I'm sorry. This is an empty F4 board. But that's not really the point. The point is that mechanically it matches. And that makes it really, really easy to figure out where to put it. Or you don't have to make any decisions. It just goes there and you're done. Okay, next one, please. I am very sorry. There is a really great schematic for this. It's just that you're not looking at it. I have it on paper, and I'll be glad to show it to anybody and everybody at lunchtime. I'm also going to put this on the DIY Audio website. But I'll sort of walk you through the important parts. Here we have a pair, or here we should have a pair, of matched bipolar transistors that are matched using the circuit board in your hands. And then there's a current mirror, there's an emitter follower, and there's an output stage. It's a pretty standard 2-stage op amp, not 3-stage op amp, 2-stage op amp. And the reason for that is we don't need Godzilla amounts of output drive because we're not driving 600 ohm transformers, we're not driving headphones, we're driving the input of an F4, which is an extremely high impedance. So to drive a high impedance, you don't need a gigundous output stage. And in fact, you don't need any output stage at all, and I don't have one. It's a 2-stage op amp. Input, VAS, out. Okay, I think that might be the last one. It is. All right, I'd be glad to handle any questions. And if they involve engineering or math or equations, we'll talk at lunch. Okay, first this guy.
Are you going to have the groups for that?
Yeah, I'm sorry, I should have said that. Of course, because there's people watching me on streaming, you know, that don't have the board in their hands. So yeah, they'll get the Gerbers for free in a couple days.
So after we match some transistors, do we then plug them into our regular transistor tester and see about the gain?
I think you're talking about current gain. That sounds like engineering to me. So let's talk about that after. The short answer is, for the 4 amplifiers that I discussed, namely Wolverine, Honey Badger, Dreadnought, Bulwark, and this one, current gain is of secondary importance. There may be other circuits where it's of primary importance, but this is not among them. Okay, this guy first. Yeah, I guess what you're hoping is for the 90 seconds that you're comparing reference versus unit, you want those two guys to be at the same temperature. You're measuring their delta VBE, and then you're praying to God that the delta VBE right now isn't tremendously different than the delta VBE on Christmas Day and the delta VBE on the 4th of July. And the answer is, for pragmatic purposes, it's good enough. It's better than what Sony has, and it's actually good enough. Okay, there was one over here.
Built an F4, and after much
review of the Form BA3 was the answer to building a front end for the F4.
Okay,
Talked about that big.
all right.
This little doohickey that fits within the box that I have with the F4 is very appealing. But like a lot of these things, any idea of what it sounds like? Sounds awesome.
I dropped my pants completely and showed you my F4. And, and my F4 is unpopulated. So, the correct answer is I do not know, but I am extremely confident because I have tested this board using, conventional engineering tests, similar to what Tom did, and it passed with flying colors.
Two things. When you buy your transistors, if you buy them in cut tape form, the odds are much, much better than that you're gonna find a lot of good matches rather than just, picking them out or buying them individually.
That's my experience too. And so the thing you want to look at on DigiKey and Mouser is the magic word ammo pack.
Right, and or cut tape.
All right.
You can buy 10 of them on cut tape and you're in good shape. The other point in using your thing, which is a great idea, is that with respect to temperature, between measurements, you probably want to, if you haven't already, turn off the voltage between the times when you're changing transistors. Otherwise, one's going to have warm-up time, or the warm-up time will be a little different. Right.
Okay, does everybody understand that remark? It's true, that's been my experience. And so when I'm talking about 120 seconds, I'm talking about pretending that you don't know that. Pretending that you are not pretending, actually measuring with the darn thing left powered on all the time. And that's just pragmatic because it's a 9-volt battery. And disconnecting a 9-volt battery is, if you're me, clumsy. And so, yeah, well, somebody designed the board without a switch. I don't know who did that.
Sad folks that have bad companies. What I use for my matcher, which is different from this one, or similar, is I made a foam cover box out of insulated foam. And then I set, on top of the air currents from the flow thing. And they can equilibrate inside this little foam cover.
Could you quote a time to stability for us, please?
For some of them, 30 seconds, and they're very stable, but I usually go 60 to 90 seconds.
Okay. So not a giant savings in time, but a big boost in confidence.
60 seconds, but also will for you.
Yeah. Yeah. But if your lab chair swivels, you just swivel 45 degrees to the left. Yep. Okay.